Let's begin. Yes, Abhinav, we will keep some time aside for the doubts from the module also. Okay, yes, we are done with integration. We have discussed integration by substitution, whatever we require at basic calculus level. And we have also discussed about definite integration and area under the curve. So now we can complete the module exercises, and we will keep some time aside for discussion of doubts of the module exercises, etc. Okay.
Excuse me, sir.
Yes.
Can I just ask you a little about the differentiation of trigonometric functions, this one?
Trigonometric functions?
Differentiation.
Yes, tell me what about it?
So when you say that d sine x by dx gives you cos x, that
Yes.
basically means that on the function of sine x, the slope of the tangent is cos x, right?
At any point, yes, correct. Yes.
So I didn't get what that means in theory, practice. What does it mean that the
Okay.
slope of the tangent is cos x?
Okay, I'll explain that. Okay, just give me. See, what it means is that you have, let's say, the graph of sine x, right? If you draw the graph of sine x, it looks like this in the first cycle, right? Y equal to sine x. Now, first of all, what it means that dy by dx is equal to sine x. Where this comes from? Now you've done enough trigonometry to understand the proof of this from the limit method. Remember what was dy by dx actually? It was limit delta x tending to 0, right? F of x plus delta x minus fx divided by delta x. This was the concept of it.
Yes, sir.
Okay, so here it will become limit delta x tending to 0 sine of x plus delta x minus sine x upon delta x. So you expand this, okay? So it becomes sine x cos delta x, okay, minus, so plus cos x sine delta x minus sine x upon delta x with that limit applied to this. So now see here, when we apply this limit, delta x tending to 0, for a small angle, what happens? Cos theta becomes tending to 1, right? If theta is small.
Yes, sir.
And sine theta becomes tending to theta for theta being a small angle, right? Because you have that thing.
So what is this you said? Sine theta becomes tending to theta.
Becomes theta. Okay, so because see, this is the angle of theta. So this is arc upon radius,
Right.
And if you drop a perpendicular over here, then sine theta is basically what? Perpendicular upon radius, because the radius is the hypotenuse, right?
Right.
Now see in this triangle what is happening. If theta is very small, then there's hardly any difference between the arc length and the perpendicular.
Yes, yes.
Okay, so we have this approximation that sine theta becomes approximately equal to theta for theta being a small angle.
Okay.
What happens? Perpendicular becomes approximately equal to the arc length. Okay, and cos theta becomes approximately 1, because what happens is that the base becomes approximately equal to the hypotenuse, which is the radius.
Okay, sir.
Okay, so when you put that in the above thing, so when you remove the limit by putting this condition that this delta x is very small, so because delta x is very small, cos of delta x is becoming what? Is tending to 1, right? And sine of delta x is tending to how much? Delta x only.
Delta x.
Okay, so this becomes sin x plus cos x into delta x, right? Minus sin x upon delta x. Now, because delta x is tending to 0 but not equal to 0, there's no problem in cancelling this and this, so we get cos x. So first of all, this is how we get the fact that the derivative of sin x, its value is equal to cos x. Okay. Okay, now what is the meaning of this? Let's understand. Okay, so we got dy by dx equal to cos x. So now let's understand this in terms of slope. Okay, so let's pick some point between 0 and 90. So let's say we have picked 45 degrees here. Okay, so if I draw a tangent over here, the slope of that tangent should be equal to what? It should be the value of cos x or of the derivative at x equal to 45 degrees. So that's how much 1 by root 2. So that's approximately 0.7. Understood, no?
But sir, what does it mean that it's cos x?
Its value comes from cos x, no? Just like see y is equal to x square, dy by dx is what? 2x. So this is the derivative of this function. So the value of the derivative at a point is basically what? The slope. So like that, cos x is the derivative of the function sin x. So at any point on the function sin x's graph, the value of the slope of tangent is what? The value of cos x at that point. So like that, for example, if you select a point of 90 degrees, what is the slope at this point? Expectedly, what should it be? It should be 0 because you've reached the local maximum.
Yes, sir.
You can see cos 90 is 0. So slope
Oh,
at,
yes, sir. Yes, sir.
so like that, now you see any point between 90 and 90 and right up to 270, you can see it will have a negative slope,
Yes, sir.
and cos x has that property that second and third quadrant cos x is negative.
Yes, sir. Okay, sir.
So that is the thing over here.
Thank you, sir.
Okay.
Sir, how did you get sin x cos x delta x plus cos x sin x delta x?
How did I get cos x sin x cos x delta? That's from the formula, no? With a sin a plus b is sin a cos b
Yes, sir. Yes, sir.
plus cos a sin b. That you've done, no? In trigonometry by now.
Yes, sir.
Yeah. Yes. So see,
सर
earlier we
आपने
had not. Yeah.
सर अपने लास्ट क्लास में होमवर्क भी दिया था इंटीग्रेशन ऑफ sin x dx और इंटीग्रेशन ऑफ mod sin x dx उसमें भी डाउट
Tell me.
सर इंटीग्रेशन ऑफ sin x dx with limits 0 and 2 pi और फिर
So how much
दूसरा
that
था
is coming?
सर
You
minus
got it?
cos x
No. So how much is the value finally coming after putting the limits? Did you do the question?
sir we needed to analyze the graphs
No, first this one you don't. Here you directly put the limit. No? So this is the indefinite integration is minus cos x. So you put the limit 0 to 2 pi. Right? So it's what? Minus cos 2 pi minus of minus cos 0. So that's how much? That's 0. Right? This is clear?
yes sir
Okay. Now you can analyze the graph and understand why it's 0, because this graph of y is equal to sin x. It's giving you this area plus this area, but this area is positive, and this area is negative, and because of the symmetry they are exactly cancelling out, so that net area from 0 to 2 pi is coming out to be 0. So this one is clear now.
yes sir
Now when it comes to mod sin x, if I'm doing the limit from, if I'm doing the integration for the same limit 0 to 2 pi, okay. So what is happening now? Mod sin x is a different function. No? Mod sin x is a function which I will define as sin x for sin x being greater than equal to 0. That means x being between 0 and pi, whereas I'll define it as minus sin x for sin x being less than 0. That is for x being between pi and 2 pi. So this definition is clear now.
Yes, sir.
Okay. So now I can also understand in terms of graph what happens. If this is the graph of sin x, how will the graph of minus sin x look like? The graph of minus sin x is this. This is y is equal to minus sin x. Okay. And this is y equal to sin x. The mod sin x is such a graph that we have to select out of this. We have to select the sin x graph between 0 and pi. Okay. But then we have to select the minus sin x graph between pi and 2 pi. So mod sin x graph will look like this. And that thing continues. Okay.
Okay, sir.
So this is now my graph of y is equal to mod sin x. So now the area that I'm looking for in this is actually this total area. Okay. So we can also understand that just by symmetry, this we can write as twice of the area of sin x graph from 0 to pi, or we can write it as also sin x from 0 to pi plus minus sin x from pi to 2 pi. Okay. Both are one and the same thing, and they will come out to be how much? They'll come out to be 2. Is it clear now?
Yes, sir. Thank you.
Okay, so this was the interpretation of this.
So this is also equal to the area of sine graph, so without the mod.
No, it's not area of the sine graph without the mod. Without the mod, the area of sine graph from 0 to 2 pi is 0. Na?
So
So
area
is
is
it equal
negative
to
sine.
sine square?
Yes, area comes with algebraic sign. So for example, if you can check that out. No? If you, for example, have a graph like this, let's say, just check a simple linear function. Okay, so let's say this point is minus 2. And this point is, let's say, this point is also, let's say, 2. Okay, so this is y equal to x minus 2. This graph is okay. Now check out the area from here to here. It should come out as a negative quantity because it's still below. So this area, when we calculate by integration, it will be x minus 2 dx from 0 to 2. You see, it will come out to be negative times the area of this triangle. So it's x square by 2 minus 2x, limit 0 to 2. So it's 4 by 2, that's 2 minus 4 minus 0 minus 0. That's minus 2. And you can see the area of this triangle has a modulus of 2, but it's below the y-axis. So it's coming out with a negative sign. Okay.
Okay,
Similarly,
so
now if you calculate the total area from 0 to 4, you can see that this and this will cancel each other. The same
yes, so
thing,
0.
if you calculate from 2 to 4, you'll see the area will come out to be plus 2. And that's why if you calculate from 0 to 4, the net area will come out to be 0. As you can see, it will be x square minus 2x. So the upper limit is also 0.
So it should be x square by 2.
Ah, sorry. Okay, so this integration, it always gives us what we call the algebraic sum of area. If the graph is alternating between the positive side and the negative side, this always gives the algebraic sum of area. It's positive for fx being greater than 0 and negative for fx being less than 0. Okay, so hope this point is also clear to all of you people.
So its graph is equal to the area enclosed is equal to sine square x graph.
So you want to calculate the area from what to what limit for sine square?
Sir, the earlier question.
0 to 2 pi.
Yes, sir.
So that we've seen in the class last time. Sine square x dx from 0
Sir,
to
should
2
it
pi.
be
That
equal?
sorry.
Sir, should it be equal?
No, because mod sin x and sine square are different graphs. You understanding, no? The shape is different. See, the value of sine square x, for example, at x equal to pi by 4 is how much? It's half, no?
Yes, sir.
At x equal to, let's say, 5 pi by 4 also, it's half. But the value of mod sin x at x equal
Sir,
to
I
pi by
understood.
4 is 1 by root 2, no? Understood, no?
Yes, sir.
So that's why the area comes out to be different. So here, if you calculate the area from this you'll have to do this 1 minus cos 2x. So this will come out to be 1 by 2x minus sine 2x by 4. Now you put the limits on this from 0 to 2 pi. So you'll see you'll get the upper limit as pi minus 0, and you'll get the lower limit as 0 minus 0. So you'll get the area as pi. So this thing sine square x dx from 0 to 2 pi, this area is pi. Okay. Whereas we just saw that mod sin x from 0 to 2 pi was giving us the value of 2. So this is a larger area. This is about 3.14. So the reason why that happens is that if you compare the graph of sine square x, it's a little bit bulging like this. Okay, compared to mod sin x, which will be like it will be more like this in comparison. Okay. Because you can see now at those type of points like pi by 4, this has a larger value. This has a smaller value. Okay, they reach the same maxima, local maxima of 1. It's also the global maxima. Okay, so there's subtle difference between the graphs. You're following now, Beta?
Yes, sir.
It's like even there's a difference between the graph of x and x square, no? Even between
Yes,
0
sir.
and 1. So like that. Okay, so let's. So as I said, like we will keep some time aside for discussion of the doubts of integration from the module also. Plus, I will keep sending you some revision exercises also as we go along. But I think this is a good time to start kinematics because, like as I said, the kinematics early part is complete application of calculus only. Okay. Calculus and vectors also, but that will come, when we discuss 3-dimensional or 2-dimensional kinematics. Okay. So first of all, what about kinematics? Kinematics is basically the physics of motion. So in kinematics, what we do is we study equations to describe and define the motion of a body, or a particle or whatever. Okay. But we don't describe the cause of motion. Okay. It's only the effect that the motion is like this. Whereas in dynamics, what you're doing in the other track of physics, Newton's laws of motion onwards, there you're understanding what is the cause of motion. Like forces acting on a particle create some net force on it. If that net force is 0, that creates acceleration. So that is causing the motion. But here we are studying that, okay, if the acceleration is so much, then how the motion should be, what kind of path it should take, how its velocity should be varying with time, how its displacement should be varying with time, etc. So kinematics is independent of dynamics in that sense. And later, of course, you'll see there's a connection between them. Okay. Now, having said that, if you talk about kinematics or motion of a rigid body, so what is a rigid body? Any body made of material that is rigid in structure, not fluid in structure. Its shape and size does not change. It does not morph. So Any object which is made of solid material such that its shape, volume, size, mass, etc. does not change with time, that is called a rigid body. Okay. So if we talk about motion of a rigid body, you will see that there are some different types of motion possible. For example, the most obvious and easy case of a rigid body motion is motion along a straight line. So in straight line motion, what happens is that the body moves in such a way that its, let's say, its center of mass, or its, if you select any point which is roughly at the geometrical center of the body, it will describe a straight line path. So now you'll see that because the body is not rotating, okay, so what will happen is not only the central point or the center of mass is describing a straight line path, but any other point in the body is also describing that same straight line path. So if after some time the center of mass is reached from here to here, that means this corner point has also reached from here to here. This corner point is also reached from here to here. So all the particles which are part of the rigid body, they're all describing a straight line path. So straight line motion for a rigid body is when the entire body, that means all the particles within it, describe or move along a straight line path. So another way of saying this is that its center of mass, of course, we haven't defined what center of mass is officially in physics yet. That will come in a further later chapter. But you can sort of understand it's like the symmetry point within the body. Its center of mass C moves along a straight line, and most importantly, the body is not rotating. It's not spinning or anything. Okay. So if it is not rotating, that means all the particles are describing the same straight line path. So this is what we mean by straight line motion of a rigid body. So I hope this point is clear to all of you. Now, another type of motion, for example, for a rigid body could be where we have what is something called pure rotation of a rigid body. So a good example of that is like how a pendulum generally moves. Okay. Or in this case, let's take a situation where imagine we have something like a plank. Okay. So it's a rigid body. There's a fixed shape and size. And then what we've done is we have hinged it over here. We put a pin about which, so it's hinged. And now this whole thing is rotating about. So it's going from here. Next, after some time, its position is like this. So now you can see there's a huge difference between what we've discussed earlier in this one. In this case, for example, the center is describing a circular path as it is rotating. And as the center of mass is describing a circular path, you can see every other point in the body is also describing a circular path. But you'll notice something very interesting, that different points are having different amount of motion. They're never moving identically. Okay. The identical thing is that they're all in circular motion, and they're all in circular motion about a common axis. But that's where the identical part stops. They all have different radii in general. They'll all therefore travel different distances in the same amount of time. They will travel different displacements in the same amount of time, etc. So pure rotation of a rigid body is when the rigid body is in rotation about a fixed axis. Okay. So what happens is that every particle is in rotation, or you can say in circular path, about a common fixed axis. So in this, one thing we can see is that different particles within the body have different velocity, speed, displacement, later we will see acceleration also, etc. at a given instant. Okay. Whereas going back to that straight line motion, we can see that every particle has identical velocity, displacement, etc. at a given instant. Okay. And of course, along with that, here what is very important is that every particle is describing a straight line path, whereas here every particle is describing a circular path, okay, with different values of instantaneous velocity, instantaneous speed, displacement, etc. at a given point of time. Okay. Now, another type of motion could be like this, where imagine again we have a rigid body.
Excuse me, sir.
Yes.
You will give us time to write after you're done, right?
Yeah, I mean, see, here now I'm just giving you a basic introduction. So you don't need to write down all these things like definitions as of now. Okay, so what is important to write down, I'll give you time to write down. And later you can refer to my notes for this part, right? Okay, you're following now, madam? Plus, now that we are starting kinematics, I will also refer you to some standard sort of reference books. So you can also read from those reference books and correlate what I'm describing here. Okay, now imagine a rigid body which is now moving like this. It's not exactly moving along a straight line path. So after some time it's reached here. After some time it's reached here. Okay. So it is moving in, let's say, if you trace the center of mass, how it's moving in a non-straight line path. But at the same time, all the time, the body's orientation is remaining the same. It's not rotating about the center of mass. So now we can see that if you take this corner point, it will have an identical path. The initial and final point may not be the same, but its path is going to be identical. So at any instant, their velocities are going to be identical. Their accelerations are going to be identical. So this happens when the body is not rotating about its center of mass as it is moving. So when a body is moving in such a way that the center of mass has a general, what we call curvilinear path, that is non-straight line. But, or you can say rather than but, you can say that and the rigid body is not rotating. Okay, or you can say it's not spinning. So when that happens, again, every particle has identical velocity, displacement, etc. at a given instant. Whereas the final, more contrasting type of motion is like, what happens, you see very often in everyday life, how rigid bodies move. For example, if I take, something like this pen, just, okay. So if I take this pen and I throw it in the air, so it will tend to have this kind of a path. So it will go like this. So while its center of mass is going in, like an expected path, like when you throw a ball or something, but at the same time, about the center of mass, the body is also rotating. So you can see that the path of the particles other than the center of mass has become more complex because they are describing circular motion about the center of mass. And while they are describing circular motion about the center of mass, the whole center of mass itself is moving like this. Okay. So what has happened here in this case is that the body is in a combination of two types of motion. One is that the whole rigid body is at any instant rotating about its center of mass axis, about an axis passing through the center of mass. But while that is happening, that axis itself is not fixed. That axis is shifting. A simpler example of this kind of motion is imagine a cylinder or something rolling down an inclined plane. So what is happening? You see the cylinder spinning, but at the same time, the axis about which it is spinning, that's not a fixed axis. That axis itself is coming down the inclined plane. So that type of motion is called rigid, it's called general rigid body motion. So we'll come back to the definitions, don't worry. So in general rigid body motion, for example, you're going to have, like the example I gave you, that you have this stick, okay, which is moving in such a way that its center of mass is being thrown in the air. So it's describing this kind of what we'll see later as a projectile path. Okay, but at the same time, about the center of mass, there's also spin happening. So as the body is moving, it's going like this. Because it's a rigid body, so it's not changing shape. Okay, it's going in. So now we can see that, for example, the path of this point over here, it is more complex. It will go like this. So it will have sort of this type of motion, or it can even be more complex than this. Okay. So in general rigid body motion, what is happening is that the center of mass is in general curvilinear motion. And simultaneously, the body is in rotation about an axis through its center of mass. Now, why the axis is always through the center of mass is also a very interesting aspect of mechanics. And the proper answer to that question will come towards the end of mechanics, when we reach rotational dynamics chapter. So what we'll see is like, all these chapters that we do back to back, kinematics, Newton's laws of motion, then center of mass, rotational dynamics, etc. They will contribute towards the full explanation of all these types of motion. From day one, we cannot write the equations for all these types of motion because we have to learn a lot of things in between. But another example is the one I told you, the cylinder as it is coming down, rolling along the inclined plane. So as it rolls, you will see the center of mass moves along this kind of path. It's moving very simply like this. But at the same time, about the center of mass, there's rotation happening. So if you see the path of a point like this, for example, it's having a very complex kind of path. You have this kind of a path. So in the ground frame, different particles are having different kind of path altogether. But yeah, if you see with respect to the center of mass, at any point of time, all the other particles are in circular motion or in rotation. Okay. So these are the different types of motion that a rigid body can achieve. Okay, let's just review them once from the beginning. As I said, you don't need to write these down. This is just a general description. Okay. You just need to understand the points I'm saying over here. So the simplest type of motion that a rigid body can undergo is the first one we took. That is, it's a straight line motion. So that means not only there is no rotation, but the path is also very simple. The center of mass is moving along a straight line, and all other particles are also moving along parallel straight lines, such that at any instant, whatever velocity the center of mass has, this corner point, for example, has the same velocity. They'll have the same velocity, they'll have the same displacement. Okay, and all other parameters like acceleration, etc. Also, when we study later, you'll see that every particle within the rigid body has the same parameters for kinematics, and at the same time, they're all describing straight line motion. Okay, so this is the simplest type of motion that a rigid body can have. Now, the next simplest type of motion is pure rotation, but interestingly, pure rotation is something that, again, like in terms of the equations and all, we'll be studying at a later stage, not right now. But this is just to give you the idea of the different types of motion. So pure rotation mein kya ho raha hai? The rigid body is completely in rotational motion about a fixed axis. The axis is not moving. Okay. So once we understand that there's a fixed axis, if we trace the path of the different particles or the different points within the rigid body, what we'll observe is that they're all describing circular motion, but with non-common value, different values of instantaneous velocity. You can see that this point will have more velocity compared to this point. This point will have less velocity because they are traveling different distances in the same intervals of time. They'll travel different amount of displacements. Okay. But all of them will be in circular motion about a common fixed axis. So when the axis is fixed, axis of rotation is fixed, then we call it as pure rotation. The term pure rotation is used for it. Then we come to another interesting type of motion where there is no rotation happening, but at the same time, the path is not straight. Okay. So like it might be a little difficult to visualize this in the beginning, but just try to imagine this. This body is basically, it's moving like this. So while it is moving, there is no rotation happening. Whereas rotation about a fixed axis, pure rotation would have been like this. But I keep one axis fixed, okay, and every particle is going about in rotational motion or circular path about that fixed axis. Whereas this one that I'm showing right now, that there is no rotation, that one is like this. The path need not be straight line. Okay, a straight line path would be like this. Here the path need not be a straight line, but at the same time there is no rotation happening of the rigid body. So when this one happens, every particle within the rigid body, yes, Bhavika, I'm coming. I'll tell you the names, okay, of the different types of motion. Okay. So when this one happens, all the particles of the rigid body have identical values of velocity, displacement. Later we will see acceleration also, etc. Okay. Whereas now the most complex type of motion, which we call the general rigid body motion, that is this type of motion. I should do that. Something like this happening. So in this, that the center of mass of the body is in a general curvilinear path. That means it's not in a straight line path. And while the center of mass is moving in its general path, the body is in rotation about it. In this one, it's slightly different. The center of mass is not in curvilinear motion, it's in straight line path. Okay. So rolling down an inclined plane, or even rolling on a horizontal surface. I've taken the example of rolling down an inclined plane. The center of mass is in motion along a straight line, whereas all other particles are in rotation about an axis through the center of mass, while the center of mass itself is moving. So in this general rigid body type of motion, you can see that the axis of rotation is not fixed. It's not a fixed axis. So that is the difference between this general rigid body motion and the pure rotation we had talked about. Okay. Now we come to the classification in terms of proper names. Okay. So further, what we do is we club together these motions into three categories. Okay. The first type of category. So classifications of rigid body motion. So the first classification is what we call pure translation. How this relates to the examples you've discussed above, I'm explaining that in just a moment. Okay. So let's first understand what is the definition of pure translation. Pure translation is the type of motion such that the rigid body is not in rotation about its center of mass. So what this means, this implies that every particle has identical velocity, displacement, and acceleration at any instant. So this includes which type of straight line motion, and which was example 1 above, this one, motion along a straight line. This is an example of pure translation because there is no rotation about the center of mass axis happening. Okay, but if you come to this second example, even about the center of mass you can see there's rotation happening. So this is not an example of pure translation. But the third example, this is also an example of pure translation because while the center of mass is not in straight line motion, but if you fix yourself to the center of mass, you're not seeing the rigid body in rotation about the center of mass. The rigid body is remaining fixed in its orientation. It's not rotating about the center of mass. So that's also an example of pure translation. Center of mass in general curvilinear path such that the body is not rotating with respect to center of mass. So both these together are clubbed together. Example 3 and example 1, they are clubbed together as pure translation. And this is the definition of pure translation. Okay, that every particle within the rigid body. Okay, so the definition is that it's a type of motion that the rigid body is not in rotation about its center of mass. But what that implies is that every particle in the rigid body has identical velocity, displacement, and acceleration. Okay, so now the most important thing is that means when a rigid body is in pure translation, its motion can be described or defined by the motion of its center of mass alone. Because every particle is doing the same thing that the center of mass is doing. It's moving along the same path exactly, it's having the same velocity, same acceleration. So in other words, what we can do, it implies that the body can be treated as a particle, as a single particle. Okay? And that's why we call this type of motion particle kinematics. Okay. So to write the equations of motion, what we can do is we can imagine we've compressed the entire body into a single particle at its center of mass. And whatever that single particle is doing, every particle within our rigid body is doing the same thing in terms of its motion. Okay, so we can reduce the equations of motion from rigid body motion to a single particle motion, and that type of motion is called particle kinematics. In fact, that is what we will be studying in this chapter. In this chapter of kinematics, though the name is kinematics, is actually only one section of kinematics where we are only dealing with situations where either we have only a particle moving or we have a rigid body moving, but it is in pure translation. So while the rigid body is moving, it is not spinning. So that means the entire equation of motion for the rigid body can be described as the equation of motion for its single point center of mass. And therefore, the rigid body can be thought of like a particle. So it might be a big object like a bus moving, but as long as it's not spinning while it's moving, we can treat the entire bus for kinematics purpose, just like a particle located at its center of mass. Okay. So hope this point is clear. Okay. Just make a note of this definition now and this
Sir,
explanation. Yes.
sir, it should be center of mass or center of motion, like above the in the last point.
Yeah, it should be center of mass. Sorry. It's one. No? Yeah, it should be center of mass. Okay.
Okay. Sir.
So you can write down the thing or just write down a brief definition of the pure translation part, but make sure you understand all the points over here. Okay. Then we'll continue further. Okay, so the definition of pure translation, I hope, is clear to all of you. Now, next thing, the second category of motion for rigid bodies we'll see is, it is called pure rotation. And this definition we've already seen above, but we will just repeat it here. So pure rotation is when a rigid body rotates about a fixed axis. So what we observe is that every particle is in circular motion. About a common fixed axis. So here the kinematics cannot be described by the motion of its center of mass alone. Therefore, the body cannot be treated as an equivalent particle. So this is where we move to what is called rotational kinematics, not particle kinematics. So this is for a rigid body. So this will come in a later chapter. And the final and third type of classification is general rigid body motion. This is the final example we had seen above. So in this, what is happening is that the body moves such that the center of mass may be, or you can say center of mass is moving along a straight line or curvilinear path. Either way, it doesn't matter. And simultaneously, okay, the body is rotating about the center of mass. So this is basically what we call a combination of rotation plus translation. So this will also come under the category of rigid body kinematics. So because it's a combination of rotation and translation, we cannot treat it as a particle. So out of the three categories, pure translation, pure rotation, and then general rigid body motion, which is a combination of rotation and translation. It is only in the first case, that is pure translation, that we can treat the entire rigid body like a particle and apply what is called particle kinematics. Okay? However, that is a simpler of the three, and that is why we will start our study of motion with the first one, that is particle kinematics. That means even if we are talking about a rigid body, the rigid body is a pure translation, so it can be treated like a particle. Pure translation, I repeat, does not mean that it's straight line motion. It can be motion along a curved path also. But while the center of mass is moving along a curved path, the body is not rotating about the center of mass. So every particle is having the same path identically, same velocity, same acceleration, same displacement at any instant of time. So right now, the important thing for us is that in pure rotation, second category, we cannot treat the body like a particle. In general rigid body motion, the third category, we cannot treat it like a particle. But it's only in pure translation that the particle can, the rigid body can be treated like a particle. So we can apply what is called particle kinematics. Okay. So while the name of the chapter for us here is kinematics, but it's not correct to understand that it's the entire part of kinematics. It is the first part of kinematics, which is particle kinematics. So here, even if we are saying that we are applying the equations to a rigid body, the rigid body we should be able to treat it like a particle. So that means rigid body must be in which type of motion? Pure translation. If it is in the other two types of motion, then we cannot use particle kinematics on it. We have to use a different set of equations, which we'll be studying later in our physics section. Within the next few months only, but later, not part of this chapter. So in that sense, you can say this is the first part of kinematics, which is particle kinematics. So now let's understand.
So could you scroll up for 2 seconds? Like, I just want to note down the last point.
Yeah, sure. I'll scroll up just a second. Sorry, just a second.
Yes, sir, done.
Okay, very good. So in particle kinematics, it's basically that we are studying the physics of motion of a particle or a rigid body in pure translation. So it can be treated like a particle. So the first thing is to understand the parameters. That is the physical quantities that describe the motion. And physical quantity is something we have understood a long time back. They are quantities that can be measured. Okay. So the physical parameters or the physical quantities, the first one is position. Now, sorry. Now, previously we might have described position by something like, coordinates or something. But now that we have done vector algebra, we will apply a vector definition to each and every one of these things. Okay. So now I'm not saying that it's necessarily motion along a straight line or anything. It's just particle kinematics. So it can be motion. It can be motion along a straight line. It can be motion in a curvilinear path. It can be motion in a two-dimensional plane, like projectile motion. It can be motion in 3 dimensions, like the motion of a fly, or a motion of a helicopter or anything that is flying, such that it moves along all 3 axes, x, y, z axis. Okay, so it can be anything like that also. So in that respect, the first parameter is position, which will now treat as a vector quantity. So the more proper definition is position vector, and we denote this with the symbol r. So position vector of a particle at any instant is described as the vector joining the origin of our coordinate frame with respect to that particular location of the particle. So this is our general XYZ coordinate system, and a certain particle P, let's say, is at the moment located at this point, which has coordinates X, Y, Z. So you have to imagine this in 3D. Then this vector, which is joining the origin with the immediate location of the particle, this is called the position vector. So one thing you can clearly understand, that the value of position vector is dependent on the reference frame. So what is a reference frame? It is nothing but the axis, the system of axis and origin. So one guy has made his reference frame over here. With respect to him, the position vector of that point is this one. But if another observer, okay, so let's say this is the coordinate frame for one person A, and another person A has made a coordinate frame which is different. So let's say this X prime, Y prime, and this is where the origin is for the other person. So they will describe the position of the same point here by different vectors. For this guy, the position will be this one. For this guy, the position will be something else. So the value of the position vector, it actually depends on the choice of reference frame, or it depends on what we have selected the reference frame as. And in general, what we mean by the term reference frame in mechanics is just a system of coordinate axes.
So the value of the components will depend on the axes. If we take the square and add them, so the vector will still be the same, right?
I can change the origin also, no, beta. You understood the point now? Like if I have thrown an object from, let's say, the 5th floor, and I'm observing as it's going towards the ground, Now I might be observing it from the 5th floor, so my origin is located there. Somebody else might be observing it from the 3rd floor, so their origin is also at a different point. No?
Sir, I'll have to think about this, because in the vector chapter, sir, we had a question also about this. The value of the which of the following will not change with coordinate axis.
No. See, there you're talking about a vector, not position vector. You understanding my point, beta? Like if you have a force vector, or if you have the velocity vector of this particle as it is moving. In fact, that's what we'll see. That those vectors will not change according to the reference frame.
But position vector will.
Position vector, because see, position vector is defined that way. No? It is the origin to that point P. So if I shift my origin, will not the length of the vector change?
Acha. Yes, sir.
Sir, but when we were talking about fully motion in vector chapter, sir said that it whether I see it from the bottom or whether I see it from the top, if the lift is going downwards, it's going that's not going to change anything. So how
Yeah,
is
that's
it
true.
depending on the reference? I'm not
So
getting that.
that's what we are going to see now. That position is only something to define position. It doesn't describe the motion really in that sense. But when we come to displacement, when we come to velocity, these are not going to be reference frame dependent. Understood my point?
Yeah, okay, sir.
Okay, so I think position vector is something which is fairly obvious and clear. Now let's come to the next definition.
So I had to note it down. 1 second.
Okay.
Okay, sir.
Okay. Okay, now next thing is displacement. So displacement, again, we'll take it as a vector here. So the definition is that it is a vector joining the initial and final position. So remember, whatever we are discussing here is in context of the particle kinematics. So even if we have a rigid body, we are reducing it to a particle. So there's no problem understanding, that what is the initial position and what is the final position of that particle. So if the particle was initially located here, so this is the initial position which we can write with coordinates x1, y1, z1. And after some time, through whatever path, it does not matter what the path is, the particle has reached here. This is the final position. Let's say x2, y2, z2. Then we know that, like from our everyday knowledge, even before we're done vectors and all that, we understand that the displacement is just the straight line. Now the only difference is, having done vectors, instead of defining it as the straight line or shortest path, we define it as the vector arrow pointing from the initial point to the final point. So this is what we will say is the displacement vector. This is the displacement vector. But now you can also see that the displacement vector has a very nice relationship with respect to these two other vectors, which are the initial position, okay, which I can write as Ri or R1, whatever, and the final position. You can see that they are forming a vector triangle where these two are joined from the common origin, the initial and final. So this third vector that we have drawn is basically the difference of these two. So the maths definition or the formula for displacement now, it becomes the final position minus the initial position, or we can just say that displacement is delta R. So in words, we can also say that displacement equals to the change in position R. As a vector definition, this is what it is. Now the interesting thing you will see is that the displacement vector S is independent of choice of frame. If some other observer is having a different frame, their Ri and Rf will be different. But the difference of the two vectors, Rf minus Ri, that will be the same. Hope this point is clear to all of you.
Yes, sir.
So you can see that if this is one reference frame and this is another reference frame, and we have the same thing. But this displacement vector is the same, no matter which reference frame you take.
So position vector is kind of like relative position sort of. You're trying to
Yes,
tell the
yes.
position of something.
It is always yes with reference to something. No? So it's relative to that one.
So relative, it's like relative velocity also, which depends on the
Yeah, that's why
person
later we will
observing.
see that if our reference frame is moving, then the position is what we call a relative position. Okay, the velocity with respect to that frame is relative velocity, things like that, right?
Yes, sir.
Now, needless to say that position and vector, position and displacement, as physical quantities, they both have the dimension of length. Okay. That's another thing you should understand. And their SI unit, okay, is meters, but we can also take it in kilometers or centimeters, whatever. So the dimension of position is length, and same as the dimension of displacement.
Sir,
Yes,
what is this diagram you drew, the last one?
it is to show you that displacement is independent of reference frame.
Okay,
The
sir.
last line that we did. So you can see now in the two reference frames, the values of the R vectors are different, but their difference is the same. It is this
Yes,
same
sir.
black S vector.
Yes, sir.
Now next we come to the definition of velocity, and this is also a vector quantity. So we'll denote it with the symbol V. So like we had defined rate of change earlier as two types of rate of change, instantaneous and average. Similarly, velocity, two types we'll say. The first is simply when we use the term velocity, by default, it means the same thing as instantaneous velocity. Okay. So from now on, we should understand that even if we don't attach the term instantaneous with velocity, the general default meaning of the term velocity is that it is instantaneous velocity. Okay, so instantaneous velocity is the instantaneous rate of change of position with respect to time. Now here something interesting comes up. that you might say that, okay, we have earlier understood this velocity as displacement upon time. So why we are saying it's rate of change of position with respect to time? But you understand that displacement only na, is change in position. No? The displacement at between any two instants of time is the change in position. So the displacement for a very small interval of time is the same as the change in position dr during that displacement. Okay. So mathematically, if you look at it, we are defining velocity as the instantaneous rate of change of position with respect to time. So in this definition, what is happening? dr, it is the change in position in a time interval of dt. Okay, but that is the same thing as the displacement ds in the same time interval. And of course, we understand dt is limit delta t tending to 0. Delta. What is dt? It is an interval of time that's so small that is tending to 0. So from now on, our simple definition of velocity, the term velocity only, we'll just understand it as dr by dt. It's instantaneous rate of change of position with respect to time. And that's the same thing as displacement upon time.
Sir, can you please repeat the last thing? I got disconnected.
The change in position dr in a small interval of time dt is the same thing as the displacement ds in that same interval of time.
Okay, sir.
Understood, no? That's right.
So can you explain how dr by dt and ds by dt are same? Okay.
Because dr is the same thing as ds, no, beta. S is defined as what? Final position minus initial position. The note that I've written in general, displacement is delta r. So what is the displacement in a very small interval? It is dr only, no? Have you understood the point now, beta?
Yes, sir.
Okay. So now when we take actual, numerical examples, this will become even more clear. Because right now you might be thinking like, how can we differentiate a vector quantity? So we'll see that also. So vector is very simple. Na? Its components are instantaneous, changing with respect to time. So we have to just differentiate them according to the function. Okay. So we'll come back to that. Now the second thing is average velocity. Average velocity is the average rate of change of position with respect to time, or we can say it is the displacement, because the change in position is the displacement only, no? Displacement divided by the time interval. Okay. So average velocity is always defined for an interval. We can't say what is the average velocity at this moment. We will say for this interval of time, from this time to this time. Whereas instantaneous velocity is always at an instant. It is not defined for an interval of time, it is defined for an instant. So average velocity, formula wise, we can see it is average rate of change. So it is delta r by delta t, or we can say it is final position minus initial position divided by whatever time interval. So final position minus initial position is nothing but displacement. So whether we call it displacement upon time for the given interval, or we just say it is the average rate of change of position with respect to time, it's one and the same thing. Because S is equal to delta R by definition. Okay, so this is just how these quantities are defined. They're fundamental definitions. Position tells you the location of a particle. So if we know the coordinates with respect to some origin, we can express that location as a vector quantity, x I cap plus y j cap. Now, like that, if a particle is moving in a certain interval of time and we want to calculate the displacement, so we define the displacement as what? The vector joining the initial to final. So according to that definition, now we are seeing what is the displacement as a formula. It is the vector difference of final position minus initial position. So it is delta r. So displacement is defined as that way. In general, velocity means rate of displacement with time. So average velocity is rate of change, average rate of change of position with time. Whereas instantaneous velocity is instantaneous rate of change of position with respect to time. It's a very
Yes.
logical set of definitions now. And now that you know vector algebra and you also know the concept of instantaneous and average rate of change in a lot of detail, so you can see that all your concepts are reducing to single formula type of definitions, that V instantaneous is dr by dt, V average is delta r by delta t, and that simple equation gives you all the information above. Okay, now the final of the parameters is the acceleration. So just like velocity, in general also when we say acceleration, we mean instantaneous acceleration. Okay, so acceleration, or in more proper terms, instantaneous acceleration. E is the instantaneous rate of change of velocity with respect to time. Whereas the average acceleration, if we denote by this kind of symbol, is the average rate of change of velocity with respect to time.
So acceleration also is also double differentiation of displacement, right?
Correct. Yes. Okay. That's another thing that you can understand, that instantaneous acceleration being dv by dt and v being dr by dt. So we can also say that A is second derivative of position or displacement with respect to time. Okay, so these are the quantities which are most important in kinematics. Okay. There are other quantities like distance and speed also, and we'll come to that. Distance, speed, trajectory, etc. But primarily in our solving of kinematics, the most important parameters are these: the displacement, the velocity, and acceleration. Position also, of course, but position is used to describe the displacement only. Okay. So, and they're pretty easy to understand and directly execute also. So we'll see a small example to begin with.
Sir, 1 second, 1 second.
Okay. Okay, this is done now, Vita?
Yes, sir.
Okay. So before we proceed with more definitions and terms, okay, let's look at one simple example. Now suppose a particle moves on the xy plane such that its instantaneous position is given by the coordinates x is equal to, let's say, 2t and y is equal to t square plus 2 at time t equal to t, where x and y is, or basically r, in meters and t is in seconds. So first of all, express instantaneous position r as a function of time. Then calculate position at t equal to 1 second and t equal to 4 second and find displacement from t equal to 1 second to t equal to 4 second. Okay. Third, find the displacement from initial, that is t equal to 0, to an instant t equal to t, and express s as a function of time t there. And then we'll calculate instantaneous velocity. again as a function of time. And its value at t equal to 0 seconds and t equal to 1 second. So let's try this out. Okay. Very simple question. You have to just put together the concepts of okay, Bhavika, just to bring your point forward, let's say a particle is moving along some kind of path like this. So at a given instant, suppose it is over here. This is where it is at time t. So at a very small time later, it will be at a very close to it, this kind of point, t plus dt. So between this point and this point, what is the change in position? Is this vector? No? So that change in position is a displacement only, no? But that displacement is very small, no? Because s is generally the displacement in a large interval of time.
Yes.
You're understanding the point? No?
Yes, sir.
So that is why in a small interval of time dt, the change in position is the small displacement dr. Okay, so this is change in position in a small interval of time or differential interval of time dt. This is displacement in that time dt. Okay. So for example, if you integrate both sides of this now, this will give you delta r, this will give you s.
Understood, sir.
Hope this point is clear.
Yes, sir.
Okay, so let's work out this question quickly.
So the particle started from origin, right?
Can't be sure of that. That we have to understand from the equation. So starting of the motion happens when at t equal to 0, no? So at t equal to 0, what is the position c?
The 2.
It's not the origin, no?
Yes, sir.
So it's 0, 2. Okay, so let's go systematically part by part on this. Okay, so I'm sure all of you are working it out. Just illustrate all the steps. Okay. Okay, so what this means is that, like, if I just go with substitution kind of thing, we can see that position at any time t is nothing but x at that time t plus y at that time t. There's no z here because the motion is in the xy plane. So the position vector as a function of time is simply this. It is 2t I cap plus t square plus 2 j cap. Okay. So for example, we can see here that the initial position at t equal to 0, even though I'm not asked this, is just 2 j cap, okay, or is the point 0 comma 2. The position vector at t equal to 1 second is 2 I cap plus 3 j cap, or is moved to the coordinate 2 comma 3 in 1 second. Then the position vector similarly at t equal to 4 seconds. Okay, so you just have to substitute t as 4 in the above equation. So it's 8 I cap plus 18 j cap. So it's like this, comma 18. Okay. So now you can, once you got a bit of a hang of this, you can try and visualize the motion also, how it's happening, how the actual path of the particle looks like. So this is where it starts from at t equal to 0. 0 comma, oh sorry, my mistake. So on the y-axis. But in 1 second, it has moved from here to 2 comma 3. So it's gone somewhere here, let's say. Then it's moved further to 8 comma 18. So it's, let's say somewhere up here. At the time it's 4 seconds like this. So the path of the particle is going to be a curved kind of path like this. So the third thing, we want to write the general displacement as a function of time. So this is basically displacement from 0 to t.
So in the second, we also have to find the displacement at 1 and 4.
We'll find that also. Okay. So this thing will be, we'll find the displacement also. I'm coming to that. Okay. So this is position at time t minus position at t equal to 0. So it's going to be this vector minus this vector. So you can see it will be this is the displacement in general as a function of time, which means that it is the displacement from 0 to t. Okay. So at some general point of time, suppose it's here.
So 2t minus 1 I cap, no?
Q minus 1 क्यों होगा बेटा? Because see what is the displacement, if this is some general time t, na, that displacement vector is this one. No?
Yes.
It does not have a, got it, no?
Yes.
This is the general displacement vector. Whereas if I'm talking specifically about the displacement from 1 to 4 seconds, then that is this one. This is the displacement from 1 to 4 seconds. Okay. So from these two, we can find out displacement from t equal to 1 to 4 is equal to position at 4 seconds minus position at 1 second. So the difference of these two will give you 6 I cap plus 15 j cap. So this is our displacement from 0 to 4 seconds. Whereas this is our displacement from a general 0 to t. Okay. Now, moving on to velocity. So we wanted to find out the instantaneous velocity and its value at 0 and 1 second. Okay. So we'll need this one. So instantaneous velocity, how we'll define rate of change of position with respect to time. So it is going to be differentiation with respect to time of this vector. Now, whenever we are differentiating a vector which is given in component form, always remember to treat I cap and j cap as constants because they are fixed unit vectors now. Their direction is not changing and their magnitudes are one each. Okay. So when we apply the differentiation, it just becomes like differentiation of 2t, this whole thing multiplied by the constant I cap, plus differentiation of t square plus 2, the whole thing multiplied by the constant j cap. Okay. So that becomes 2 I cap plus 2t j cap. Okay. So this is the velocity. And because our x and y were in meters and time is in seconds, so dr by dt of velocity is in meters per second and t is in seconds. So this is the formula of instantaneous velocity. So velocity at t equal to 0, we can see the initial velocity so called is 2 I cap. It has a magnitude of 2. Instantaneous velocity at t equal to 1 second, for example, is 2 I cap plus 2 j cap, or the magnitude of this velocity is 2 root 2 meters per second. Instantaneous velocity at 4 seconds is 2 I cap plus 8 j cap in meters per second. Its magnitude will be accordingly.
Sir,
Yes,
sir, I had got this answer wrong. I had differentiated but not considered I and j. So why do we consider I and j?
because they are unit vectors, no beta. So they are different directions. No? We cannot see 2t I cap plus t square plus 2 j cap is not 2t plus t square plus 2. No, one is along the x-axis, the other is along the y-axis. You understanding, no?
Yes, sir, but is it given that they are perpendicular to each other?
It is, no? I cap and j cap have that standard meaning, no beta.
No, in the question.
I mean, if it has that standard meaning, no? Wherever, see, like in a question, if something is given as in meters per second, then we understand that meters per second has that standard value, no? 1 meter is defined as a unit. So like that, I cap is defined universally as the unit vector along the x-axis. J cap is defined universally as the unit vector along the y-axis.
Sir,
Following
but
my point?
did we know that 2t and t square plus 2 were perpendicular?
That's what I'm saying. It's 2t into I cap, na? And it's t square plus 2 into j cap, na? So they are perpendicular to each other.
Yes,
See,
sir.
what is a I cap? Na? It is a vector of magnitude a along the x-axis. And let's say this is b j cap. This is a vector of magnitude b along the y-axis. So obviously, if I write a I cap plus b j cap, it's a universal understanding na, that this vector and this vector are perpendicular to each other. Na? You
Yes,
understood
sir.
the point? Na? It's a
Yes,
simple
sir.
vector addition. Na? Okay. So basically see what is happening here. It's a two-dimensional motion. You can see in the diagram that we had drawn earlier that the particle is moving along this kind of path. No? So we know that the velocity at any instant is going to have two dimensions. It's going to have two components. So that way also we can understand. No? So now what will be the x component of velocity? It is the rate of change of the x coordinate. No? What is the y component of velocity? It is the rate of change of y coordinate. So accordingly, what is the velocity? It is the rate of change of position. If you just compare these equations, they are just the components of this equation. This is the components of that.
Yes, sir.
Okay, so this is how the concept of rate of change applies on vector quantities. Hope this is clear. Or likewise, if I had asked acceleration now, then we would be differentiating the velocity, and we'd see that the x component of acceleration would be 0 because the x component of velocity is constant, whereas the y component of acceleration would have become 2 because the y component of velocity is 2t. Okay, but anyway, this question ends over here. Okay, so we come to an end for today's lecture. Next time we will understand very interesting things like distance and speed and how they're different from displacement and velocity. And one has to be careful when it comes to calculation of these quantities. But before I conclude, I also want to quickly go through a special application of these equations, which is kinematics along a straight line. So if we reduce all this to motion along a straight line, then what is happening is, like, let us say, let the x-axis be along the line of motion. And the motion is actually, we have selected our x-axis because reference frame is always, a choice of the observer. He or she can select the origin wherever they like and the XYZ axis wherever they like, as long as they are mutually perpendicular, of course. Okay. So by that definition, let us say that the motion is happening along a particular line and we have selected that line as our x-axis. Okay. Then what we are writing as position vector, we can just write as a single coordinate instead of I cap. Okay. What we are writing as displacement, we can just write it as delta x. What we are writing as velocity, we can simply write as dx by dt. Okay. Or that is the same thing as ds by dt. Because if s is delta x, that means ds is equal to dx. And what we are writing as acceleration vector, which is dv by dt I cap or d2x by dt square j cap. We can simply write that as so what we do is we use a scalar notation because it's along a straight line. So this is the scalar notation for what we call 1D motion or kinematics along a straight line. Okay. Because all the vectors are aligned along the same unit vector I cap. So we can skip writing that I cap as a common thing all the time. This last one should be I cap, sorry, not J cap. So instead of using the vector notation, we can use the scalar notation. So vector notation becomes optional here. But in non-straight line motion, it's compulsory. And further, it is a matter of calculus that when the acceleration is uniform, then we have these relations that v is equal to u plus at, s is equal to ut plus half at square, and v square is equal to u square plus 2as. Okay, so we will also be looking at the extensive application of this in various things, including motion under gravity, free fall motion or straight line motion when you throw something vertically upwards. And we will also be looking at these from calculus, from the application of calculus. If A is uniform, basically, you can see that dv by dt is uniform, constant. So that means V should be a linear function of time. Okay, and that's what this is showing. And if V is linear, that means, sorry, S should be quadratic. And that is what this is showing. Okay, so more about this in the next lecture. Okay, and I will also keep aside some time for discussion of doubts from the module for integration and all. Yeah, I will send a list of reference books. Okay, we'll be sending an official list of reference books also. But basically with kinematics, kinematics onwards, we'll also be doing H.C. Verma along with the module exercise and the worksheets. Okay. Apart from H.C. Verma, I will also send the names of some books which you can use for additional reference, which are optional.
Sir,
Yes.
so by when can we collect the booklets from the center?
Which center are you in, beta?
Sir, Thane.
Wait. Who's?
Sir,
Yeah, say
Ibrahim.
again. Ibrahim, no? Yeah, the second set of booklets, no? They will be coming soon, beta. I'll inform you. For NLM and all, no? They'll be coming sometime this week. I'll inform you.
Yes.
Okay. Okay, that's it for today, people. Thanks for attending. Wish you all the best.
Thank you, sir. Bye, sir.
Bye, people.
Thank you, sir.
Yes, sir. Bye, sir.
Bye, sir. Thank you, sir.
Bye, people.